Traditionally, aircraft wings have to withstand bending, torsion and transverse loads. If ribs take care of shear loads and spars are primarily focused on bending, how is torsion dealt with by the structure? If a wing only has a single spar, as shown in the drawing here, it is easy to see that it has a low resistance against torsion. This is why most wings have at least 2 spars. But what happens is that due to torsion, differential bending takes place, with the rear spar bending upwards and the front spar bending downwards. The spars already have a good resistance against bending. To take up torsion, a torsion box must be formed such that the wing skin panels and the spar form a closed cylinder as shown here. A torsion box is a closed section and has a high resistance to bending. It does not necessarily have to be circular as long as the cross section is closed. If we look at a square cutout of a cylinder loaded in torsion, it deforms into a diamond. Cylinders have the best resistance to torsion and, when loaded in torsion, pure shear occurs, hence the diamond shape. In the 1930s, attempts were made to design aircraft wings with circular spars. The British-built Blackburn-Duncanson had a single circular hollow spar that also acted as a fuel tank. However, this concept did not really take off, as the required dimensions of the cylinder for larger aircraft would be too great to fit into the required aerodynamic wing profile. The concept of a closed torsion box remained. A wing structure can very much be seen as a closed box and these days consists of a thicker skin, which takes up the aerodynamic forces, closes off the upper and lower part of the torsion box, and also partially takes on the role of the spar caps. As a result, the spar caps are thinner and degenerated. This results also in a thicker spar web, allowing it to perform the bending function as well as be part of the torsion box. Stringers help to support the skin and partially take over the role of the spar caps. And finally, the ribs are used to close off the sides. The advantages are that a wing is now a free, load-bearing structure. No additional support or strut is needed. See for instance my favorite aircraft, the Supermarine Spitfire. Another advantage is thinner or longer wings and the ability for designers to engineer the bending and torsion stiffness separately. And finally, of course, it leads to a lower weight. If we then look at a modern aircraft wing, such as the Dutch Fokker 100 as depicted here, we can see that we can now optimize the wing per local load case. Another thing to note here are the openings in the wing for inspection holes, etc. Inspection holes are important as we must be able to inspect aircraft for the damage during their lifetime. This means more reinforcements in the lower wing and more ribs. Modern wing structures are in effect a form of teamwork, much like engineering itself.